Da, go ahead. You can start.
Okay, thank you. Okay, I'm very honored to give a talk here to share our work, improving transformers with dynamic composable multi-head attention. I'm from BOPT, and the other guys are from Colorful Clouds. It's a startup in Beijing, and first, I want to give a very quick overview of some background and what we did. And we do model architecture and especially for large language models. So what is an efficient model architecture? We have a very important criteria. Let's see these curves are for different model architectures. For example, this purple one. If we train a model, for example, a 1 billion parameter model with some data, we can get a loss. And if we use a larger model, for example, 2 billion parameters, and we use more data, that is, we use more compute, we will get a smaller loss. So we use different compute, we can get different loss, and we can draw a straight line. If we use log scale, we can draw a straight line. So a more efficient model means we can use the same compute and we get lower loss, right? For example, the purple is better than the green. And that is what we call performance compute ratio. In short, we want to get better models with less compute. It is effectively the efficiency of turning compute into intelligence. And another criteria is scalability. And that means when we use more and more compute, how well can the ratio keep? For example, we want the we want the line to be like this, but we don't want the line to be like, for example, to be like this. That means when the model gets larger, and the improvement becomes small, and this is not a good. So what we propose is a new transformer architecture. So you know, transformer is now the de facto backbone for most large language models. For example, the Llama. And we improve the transformer architecture to get better performance compute ratio. And we increase the ratio from 1 to nearly 2. And for scalability, when the model is larger, for example, if we train a 7 billion model with 300 billion tokens, and that is a very large model than this model one. And the performance gap, the performance improvement becomes larger. Yes, becomes larger. Okay, so what we the improvement we made on transformer architecture, we know that a transformer has two major components, MLP and multi-head attention. And MLP is relatively simple. It is for channel mixing, and multi-head attention, MHA, is for token mixing. Token information exchange between tokens. It is the key component, and it is responsible for some very important tasks like in-context learning and reasoning. And and this is the focus of our work on the MHA module. So the basic idea is simple. We just make the QK and OV circuits. I'll explain later what are they. We just let the fixed bindings between QK and OV circuits, and they are fixed bind in MHA, and we make them dynamic bind. For example, QK1, tangent head 1's QK can connect with a tangent head 2 OV circuits. And so in this way, if MHA has H tangent heads, in our new module, we can have as many as H times H heads, and that is very roughly speaking. Okay. So I will include 4 parts. First, a motivation of what's the problem with multi-head attention, and the second is what is our design, and some evaluation. In the transformer, we can think, what does one attention head do? It has 4 weight projections: W, O, W, Q, K, O, and V. And W, Q, and K, if the input multiply with WQ and input multiply with WK, and they make a dot product, we can get a attention pattern, attention pattern. It decides the information flow. For example, which token can attend to which token, the information flow. And on this information bridge, the WX multiply with WV, and then WO decides what information or what attribute is retrieved from here, from the attended position to the destination, to the residue stream of destination, and finally to predict the next token, right? So it is just like a SQL statement. If you are familiar with this, we have where statement to look up information and from some table, and we have a select statement to get some attribute. For example, a student, the department of a student is just like the QK circuits for lookup and the OV circuits for attribute retrieval. So here are some classical music, the induction head, for example, here Mr. D and its QK can attend to URS, and its OV move the URS to here and predict the next token. So what's the problem with this QK and OV circuits? The problem is that the QK and OV are fixed binded to a particular attention head. And let's see some example. For this one, we gave the model this sentence: John has a pen, omit some text, and John has a, then the model predict pen. How does the model do this? Let's suppose it use a head, and the QK circuit will attend the pen because they use the same subject. We call this same subject QK. Yeah. And then the OV circuits copy this pen token here and predict it. That's easy. So another example is an apple is a kind of the model predict fruit. Here the QK circuits attend to the subject, and the OV circuits is not copy. It retrieve the kind attribute. For example, the fruit is apple's kind, and use this attribute to make the prediction. Or the pen is used for writing. Here is another OV circuit. So if we make this sentence, John has a pen, John has a kind of to do this task, the model has to use the same subject QK and the kind of OV. They are from head A and head B, right? Head A's QK circuit and head B's OV circuit. But there may be no such head in the model that has A's QK and head B's OV, so a model cannot do this right. Similarly, for this kind of example, the model can also can't do it. So this is why the model can do the simple task, and it lacks a composition of QK and OV circuits, so it cannot do the task below. So let's see what we do to solve this problem. We want to compose the head, compose the QK and OV circuits of attention heads. In the transformer computation graph, there are several levels that we can do the composition. For example, in the output, attention output, in the QK-OV weight projections, or in the attention score. And we do the composition here. Before we use Q and K to compute an attention score, and this is called this is attention score, and we make a soft max normalization, and we get attention weights, and attention weights is multiplied with the value. So we compose with the attention score and attention weights here. And how do we compose? Let's see this example again. John has a pen. John has a kind of. Suppose and a head 6 has the QK circuits. It can attend to pen. And suppose head 4 has the OV circuits. It can retrieve the kind of attribute. So suppose there are 8 heads, and so every head will compute attention score with the QK circuits. For example, head 6 attention score is computed like this. And in normal DCMHA, this score will be used to move the information of has 6 OV circuits, but its OV circuits is not the kind of circuits. So what we can do, we can make some transformation on this attention vector. It is composed of the 8 scores. We make transformation to make the attention vector from this to this. This position has a large value, so it can use attention had 4 OV circuits. In this way, we effectively composing attention has QK circuits and OV circuits. That is, we first compute the attention score by QK circuits, then reassign them to OV circuits. So how do we transform the attention vector? The most general way is we use a matrix. We multiply it with a matrix, right? So we call such matrix composition maps. For example, if we have this composition map and multiplied with this attention matrix, and we will get this. It is very similar to what we want, right? So we can have different attention composition maps to implement different functions. And in our paper, we proved 2 theorems that said, here, if we use the same composition map for all the attention vector, because there are many attention vectors such as between off and pin, off and join, kinds and join, has and has, and many other. For each pair of query and key, there is a vector. If we use the same composition map for all these vectors, we call it static composition. And the theorem said for static composition, it is equivalent to expanding the QK projection dimension or expanding the OV projection dimension, and that will increase the expressive power of the model. So this is our architecture for DCMHA, dynamically composable MHA. We just use a compose operator. The compose operator is responsible for transform attention vector to a new one. And we insert this compose operator into the computation of MHA. We insert 2, one before the softmax here, and one after the softmax here. So I mentioned previously what is static composition, and we want more. We want the composition to be dynamic. And why we want dynamic? For example, if we have these 2 sentences, in the first one, we need to compose same subject QK with kind of OV, and in the bottom, we want to compose same subject QK with used for OV. We want to compose different QK and OV circuits on different input. So dynamic means we must make the composition map input dependent. But there are a composition map for each pair of query and key. So there are in total T plus S. T and S are sequence length, number of tokens, right? So we need T times S composition maps. Generating and storing these composition maps directly can be very expensive. So we must solve this problem. What we use is decomposition. We decompose a composition map into 3 terms. One is a static term and a low rank term. It is the outer product of 2 smaller matrix and 1 diagonal term. It is the diagonal embedding of a vector. The last 2 terms has very few parameters, so they can be generated dynamically. And the first term, we make it static. Why will this decomposition work? First, we believe that we observe that head activation in transformer is usually very sparse. For example, in a layer, only a very small number of heads are active. So their way of composition should also be limited for a particular particular pair of query and key. And so we can use the low rank representation. It is also used in many papers to compress or accelerate neural networks. And for the diagonal component, it is the gating, right? Each head will be enhanced or depressed, and gating has proven to be useful. So here is our compose operator. It is a bit complicated because it is divided into several parts. Let's introduce one by one. First, the static one. Yeah, right, the static one. And a low rank component. And a diagonal component. The low rank component is for cross-head interaction. And the diagonal component is for gating, for head self-excitement or inhibition. And we use the query vector. Query vector is here, the input to MHA. We use query vector to generate these, we call them dynamic weight. We use some small parameters or some small networks to generate these dynamic weights. And we use the key vectors to also generate these dynamic weights. The query and key operations are symmetric. So there are in totally 5 terms. And finally, we sum these 5 terms and get the final result. This is our compose operator. This is equivalent to a tensor decomposition. We are decomposing the 4-dimensional composition tensor into 5 terms, and we use 2-level decomposition. One is row plus column composition, and the other is low rank plus diagonal decomposition. This is equivalent to this, so I will not going through the details. It is straightforward. So due to this decomposition, the DCMHA is very lightweight, and the overhead, that means the additional parameters and the additional computation introduced are relatively small. And the larger the model, the smaller the additional parameter and computation. But the performance we does not sacrifice performance. The performance is same as using the full composition map. So here, so this is the DCMHA. Now we can see the results. First is the scaling law results. We train DCFormer. We train DCFormer and transformer from 400 million parameter to 7 billion parameter model. And from these curves, we can get 2 conclusions. First, DCMHA improved both transformer and transformer plus plus. What is transformer plus plus? It is the strongest transformer architecture, which includes 2 modifications. One is rotary position encoding. The other is 3 GLU MLP, and they are considered very effective modifications. So this architecture is used by many open source models, for example, the Llama model. So DCMHA can improve both transformer from this blue line to this blue line. And it can also improve transformer plus plus from this green line to this green line. And the improvement of DCMHA is larger than the rotary position encoding plus 3 GLU MLP at this scale, 1.4 billion scale. So first we have transformer, then we have transformer plus plus, a step forward, and then now we have DCFormer plus plus, another step forward. And we also do 0-shot and 5-shot evaluation on some common downstream NLP tasks. These are commonly used to evaluate large language models. And we can see that as the model increase from 2.8 billion to 7 billion, the relative improvement become larger, right? So DCMHA is a scalable architecture, and we can also see that DCPasia 7 billion is better than PASIA 12 billion, right? On most benchmarks. But although DCFormer has better performance, it introduced some overhead in practice at training and inference. So we measure the overhead, and we find that the overhead gets small when the model gets large. For example, at 7 billion scale, the training overhead and the inference overhead is not very big compared to the improvements in performance. And the overhead is mainly caused by I/O because the compose operator do a series of operations on the attention matrix and reads the matrix into the SRAM and do some computation and write it to the HBM and read and write. So it is I/O bound instead of compute bound. And it is the same problem tackled by the flash attention. And in the ablation study, we want to know in these parts, which part are most important for the results. First, we can compare the static part and the dynamic part, and we found that the dynamic part is much better than the static part. The baseline is transformer ++, and DCFormer ++ is using only the dynamic projection. And in the dynamic projection, the crosshead projection, this one, is better than gating. This is also intuitive. And in DCMHA, we do two compose. Before softmax, the pre-compose, and after softmax, the post-compose. We can see that the post-compose is more important, probably because it is nearer to the final output of the attention model and have larger impact on the final results. And for the query and key wise, we can see that both of them can get very good performance, nearly as good as DCFormer. And query wise is a little better than key wise. Based on these ablation results, we explore several trade-offs between performance and efficiency. The first trade-off is we can use only the query-wise component. Yes, we can use these two branch. The second trade-off, we can use more local attention layers. For example, 3 to 1 means we use 3 local attention layers and 1 global attention, and 3 local attention and 1 global attention, interleaving them. Using these two optimizations, the performance of the model get little degradation compared to the default configuration. But the speed improves very much. For example, the training speed and the inference speed both improve. And finally, we want to know, in the beginning, I use some examples to show what's the problem with transformer MHA. So is DCFormer really good at these examples? So we make a synthetic data set composed of such test case. And there are various QK patterns and OV transformations, and these tasks are constructed by making various combination of this QK and OV. So we form this synthetic data set. And we test DCPHA and PHA 7 billion on this data set, and indeed, DCPHA is much better than PHA on it. And this is the result of few short learning. Also, DCPHA is much better than PHA. On every shot. And finally, let's discuss some limitations of our work. And first, our training code is optimized on TPU with JAX. We also offer training code with JAX on GPU and PyTorch on GPU, but the code is not optimized. In particular, we do not apply any flash attention like kernel fusion techniques. So the training on TPU may be slower. And for adoption of our DCMHA module, currently we train a new model from scratch. Can we adapt an existing model, for example, Llama, to use the DCMHA? We make several experiments. We simply fine-tune Llama by replacing MHA with DCMHA does not work well. So we must explore other methods to do this kind of adaptation. This is one of the future work. And another future work, also the limitation of current work, is we only compose within a single layer. But the limitation is that sometimes these two heads, for example, the QK, the same subject QK and kinds of OV, if are in the same layer, we can compose them. But if they are not in the same layer, we cannot compose them in our current framework. So cross-layer composition is another future direction. Okay, that's all for my sharing of our work. Thank you. And there could be any questions or discussions. Thank you very much.